Okay, so let's get started with our examples for visualizing vector fields. The let's see here. So the command is, well, as the name implies, it's vector field with capital V, capital F. So you can specify here the vector field components between straight parentheses here. See a couple of options here. And you can also specify a viewing window, as you'll see later. Let's just plot a couple. Actually, let's start with the one we did as our first example, which, if I remember, it was x minus y, x plus y, the two components. So you can control, I'm not going to get into that, but you can control probably the sample of the vectors given here. So the default, there is a default essentially sample of points that Maple tries to give you in a viewing window, which is again chosen by default. And I think I didn't play with this too much, but you can also change the viewing window, make it, for example, larger by specifying the range for both x and y. Oops, there's a comma here. And then you have a larger sample. Okay, so it's pretty self-explanatory. Each of these arrows is a vector that is going to be given by the function at the point in question. So for example, it looks like a horizontal vector here corresponding to probably the points where x is equal to, that's going to be the y, x equal minus y. So whenever x and y are opposite to each other, x plus y is 0, which is the reason why you see this arrow horizontal, because the y component is 0. And then to the contrary, if x is equal to y, so if you look at the points on the line y equals x, then the first component is 0, so therefore all the arrows are vertical, either upward or downward, depending on the sign of the y coordinate. The sign of the y of the second component, x plus y, on the vector field. So I mentioned, excuse me, I mentioned also the vector that doesn't depend on the vector field that doesn't depend on one of these, x or y. So x and x plus 2, that was my example. So if I sketch this, I should see all the vectors the same on any vertical line, right? Because it doesn't depend on y, so as I change just y, the vector should still be the same. Consequently, if I make the vector field to depend on y only, let's make it more general. Let's say y squared and, I don't know, let's say y plus 2, the second component. Doesn't matter how these arrows change, they will stay the same on any horizontal line. Why? Because as x changes, the vector doesn't change. It only changes with y, as you can see here. Let's actually make it very a little bit less. And actually, let's let Maple choose the viewing window. Because I think you may see a better sample. Okay, so same vectors on any horizontal line because it doesn't depend on x. Let's look at the vector field in 3D. Let's start with a constant vector field. So let's say the vector field returns, let's say 1, 0, 3. Then the viewing window is going to be a box, obviously, right? Because this is a 3-dimensional vector, but because it's a constant function as a vector field, no matter which point you pick in the domain, no matter which x, y, and z you pick, the output is the same vector, 1, 0, 3. Okay, so I hope it's pretty self-explanatory. Let's do the one for which only the third component is actually fixed. So let's say, I mean, in the notes I mentioned x, y, and 3. Let's make it a little bit more complicated. Let's say, I don't know, x minus y, comma x. I want to emphasize that these components can be anything in terms of x and y. So the second component of the vector field can depend on x, on y, on z, or anything, any combinations of the three. But in this case, we have all three depending on x and y, and the third one constant, right? The third component is 3, which is a constant. So as you can see here, the arrows change with x and y, right? The magnitude changes. The only thing that is common is going to be the y component. So all of these vectors, if you measure the height, let's say, that's going to be always 3. Okay, if you look at it from above, their magnitude obviously change. Oops, my hand slide here. So if you look it from above, that is to say, if I hide the effect of the z coordinate, obviously the vector will change with x and y. They become larger, let's say, for various combination of x and y. But what all of them have in common is the y component, right, which is 3, right? So they're all up by 3 units. I'm not sure if it's easy to see, but that's the idea. Slightly easier to see is if you have the first two components constant. So let's say 1 and 2. And the third component, let's make it simple. Let's make it z, so that it just increases with z. As z increases, obviously the vectors becomes more and more stretched up and down, right, with positive z. What all of them have in common is, like I said, the x and the y component, which means that, again, if I look it from above, and if I hide the z coordinate effect, I should see the same vector, 1 and 2. It's kind of flipped here because let me see if I can, so that I can make the positive y upward and actually like that. Let me see here. No, I don't rotate it. I want to have x on the bottom, and then y just a second. One more. So I want x to increase to the right, and y no. There you go, finally. Yeah. I wanted to have x, positive x to the right, and positive y up, right? So seen from above, hide the z effect, and now you see the same vector, 1 and 2. Now, I mean, obviously here it's the viewing window as it cuts, the one on the last row here, but all of them are the same, the vector 1 and 2, x equals 1, y equals 2. Okay, and let's do a gradient field. So I'd already entered it here, actually. Well, I didn't. Let's use the one that I actually have in the we talked about in the previous notes. So the yeah, let me eliminate this one. So in the previous part, okay, on paper we talked about the scalar field square root of x squared plus y squared, right? So this is the function of two variables, right? So it's a scalar function, square root of x squared plus y squared. And here and I attached the graph in P1. Here I sketched the contour plot. So remember, the contour plot will give you the level curves. Remember, these are the curves of a given value. So you have the scale here nicely, right? The redder the curve, the higher the value is. So for example, if you if you hover over the level curve, it will give you the value as well. So for example, over here, this circle here, that's going to be the curve for which, or the region for which the function is equal to 9.43. So these are the level curves. And they are very easy to see that. It's very easy to see they are circles, right? Because if you set this function equal to a constant, you're going to end up with the equation of a circle. And again, the color coding is that the more the reddish hue, the higher the value is. Now let's sketch the gradient field. So I'm gonna enter here the derivatives, partial x, partial y, in the form of a vector, and ask Maple to do sketch the vector field. And these are the samples of the arrows, right? So remember, the meaning now is also the fact that each arrow indicates at that point the direction of the greatest change of f of xy. So when we sketch these two together, the contour plots and the vector field, and again, in this case, it's pretty easy because it's all symmetric. We know already the values increase along the radius, right? But it confirms what I was talking about, how useful this map is, right? So you have a sample of the values of the scalar field. You also have a sample of the points with the directions of the greatest change direction for that scalar field. So a superimposition between the gradient field and the scalar field representation. In fact, as my last example, let's actually do a more general vector field. Let's say to change the powers a little bit so that it's not a perfect circle. Let's see what happens if I make, let's make it define actually for all. Yeah, let's play around a little bit with this one. So let's make it so that it's not just a circle. So that's the shape if I just change the power, x squared plus y third, and then just change it here as well. And then all together here. Yeah, so that's a variation of the same thing. Let's actually let's see what happens here. I didn't actually run this before, just to play around with this. What if I make x squared minus y here? It's not going to be defined for all points, obviously. Neither the previous one, because there are points in which this is going to be negative, so you cannot have a negative under the radical. So that's the vector field, no, the gradient field, and the vector field x squared minus y. Okay, and then all together, and there you go. Okay, I think it's pretty straightforward, right? Here the level curves are parabolas, basically, right? If you set this equal to a constant, you're going to end up with a parabola, and then the arrows will give the direction of the greatest change on those level curves. So I think that's it for this introductory section. So I'll see you next time. The next topic will be the concept of a line integral. We're going to get straight to the applications after that. So that's it for today.